xn are Boolean variables, and each clause is, take C1, it is the OR of 3 of the variables or the negations. So for example, C1 could look like x1 or x2 bar or x3 and so on. So it could involve the complements of the Boolean variables or the original variables. Each clause has exactly 3 variables, literals in it. These are variables or their complements are called literals. The 3 CNF formula, which means every clause is exactly of size 3. And what you want to figure out is whether there is an assignment of zeros and ones, false and true, to the Boolean variables, which will make the formula evaluate to 1. So you know how the conjunctions, the Boolean operators work, and or. True or false is true. For and, we know that only true and true is true. Okay, so for the formula F to evaluate to true, there must be an assignment to the Boolean variables which makes every clause evaluate to true. And the problem is to check if there is such an assignment, and that is the 3-SAT problem, and it's NP complete, which basically means that if this had a polynomial time algorithm, polynomial in the size of the input, which is m plus n, something like that, then p would be equal to np. So you don't expect that it has a polynomial time algorithm. On the other hand, there is a trivial 2 power n time algorithm, 2 power n times some small polynomial time algorithm. So 2 power n time algorithm is simply going to look at all the 2 power n truth assignments and check if there is one that satisfies the formula F, makes it true. Okay, it's not difficult to beat the 2 power n bound. So the game is, and that's the game for the talk as well today, is to get faster and faster algorithms. Okay, it's NP complete rules out that there are polynomial time algorithms, but I want to get as fast an exponential time algorithm as possible. For example, it's not hard to come up with an algorithm that has running time something like 1.732 to the power n. How does that work? You know that, okay, so let's just go through that because it's interesting. It's somewhat, and ideas there are also present in the random walk based algorithm. So here, so let's say that there is suppose an assignment A to the n Boolean variables, which is basically a 0, 1 vector. A is an assignment which satisfies F. Okay, so A is a satisfying assignment for F. Let's fix it. We don't know it, but let's say it's some fixed satisfying assignment. Then if I start at an arbitrary assignment, let's say B is an arbitrary assignment. Let's call this A star, okay? Unknown but fixed. Suppose I start at an arbitrary assignment B. I check if B is a satisfying assignment or not. If it's satisfying, then I'm done because I found a solution. If it's not satisfying, how far am I from A star? How far in Hamming distance? How many bits do I need to flip in order to get from B to A star? That's the Hamming distance. Thinking of them as n bit vectors, how many places they disagree. It could be as bad as n. Okay, so the distance between B and A star, I know it's something that lies between n and 0. When is it n? When B is just the bitwise complement of A star. Of course, that's also a good situation because whenever I have a B, I can take the bitwise complement and check if that is a satisfying assignment. So in some sense, it's also close because of Boolean nature. But it could be like this, it could be really far from A star. But is it possible for me to start at a place which is not very far from A star? Give an assignment randomly, but a simpler thing would be to note that either A star has more than 50% ones or 50% zeros. So either the all zeros vector is a distance at most n by 2 from A star, or the all ones vector is a distance at most n by 2 from A star. Okay. So if I can start at an assignment B, which is a distance at most n by 2, then it's possible to look for a satisfying assignment in time 3 power n by 2. I can search for a satisfying, I'm searching for actually for A star, that unknown satisfying assignment, or I'm going to analyze my algorithm as if I'm searching for A star, but I'm really looking for a satisfying assignment. So there is this target satisfying assignment A star. I'm starting at B, which I know is going to be at distance at most n by 2 from A star. What do? If it doesn't satisfy my formula, one of these clauses is falsified by that assignment B. So if FB is 0, then some Ci is 0 by B. That is, if I evaluate according to B, some Ci is 0. That's why it's not satisfiable. On the other hand, I know A star is a satisfying assignment, so it must satisfy at least one of these variables in Ci. So how do I get closer to A star? Anyway, I know that I have to satisfy Ci. There are three ways of satisfying Ci. I can flip any of the three variables that are present. Let's say Ci has x1 is x1, x2 bar or x3. B is 0 at x1, 1 at x2 and 0 at x3. So what I can do is branch three ways, either set x1 to true or x2 to false or x3 to true. I know one of these branches takes me one step closer to A star. So I need to do this. So I've now found I've moved from B to a new assignment B1. B1 may be bad in many other ways. It may be bad because it has set some other clauses to false. I don't care. I know that on one of the three branches I have taken one step closer to that unknown A star. So if B1 is not satisfying, if it's satisfying, I'm done, I stop. Otherwise, I'll again pick one clause which is falsified and branch three ways. I know I'm again taking one step closer to A star on one of the three branches. So I have this three-way branching tree starting at B, and that is of depth at most n by 2. I know somewhere here A star is sitting. And I'm surely going to find that if nothing else. And square root of 3 is precisely that. Okay, so it's possible to aim for algorithms that have faster and faster running time than this, and the algorithm that we are going to describe is something that has running time essentially 4 by 3 to the power n times n square or something, or maybe n cube. Okay. And it's a randomized algorithm. So it has some exponentially small probability of error. So here, this B that you'll choose is either the all zeros vector or the all ones vector, and you'll run this algorithm starting from the all zeros or the all ones. If you don't find a satisfying assignment there, you say formula is not satisfied. Either the all zeros vector is within n by 2 of any assignment, or the all ones vector is within n by 2 of any assignment. Given any assignment, one of the two is within n by 2 of that.
Yes, but the variables you've been setting, they might be making the distance more.
I know on at least one of the branches I am getting one step closer. The total number of nodes here is 3 to the power n by 2. And at least one of them I am getting one step closer. I am suppressing the polynomial factors. There are 3 to the n by 2 leaves here potentially. So internally there is less than half of that, okay, some 1/3 of that. Okay, so what we want is basically a similar theme, but it's a random walk based algorithm. So we're going to quickly recall a very basic concept in random walks. It's a so-called random walk on a line. It's also called a one-dimensional random walk. It's a discrete random walk problem where the setting that we are interested in is you have basically this undirected path with n plus 1 nodes labeled 0 to n, and n is kind of absorbing state. So the goal of the random walk is to get to n. Essentially, n stands for getting to a satisfying assignment and stopping. Okay? That's what you want to do. And 0 is a reflecting barrier, reflecting state. That means when you hit 0, you're going to bounce back to 1 and keep moving. Okay? So when you're at 0, you will take one step to the right, always. Okay? When you're at any other node j, you will flip a coin, and with probability 1/2, you'll take either one step to the left or one step to the right. That's a random walk. Okay? And when you hit n, you just stop the random walk. So a different version of this is called the gambler's ruin problem. It is often discussed in probability texts, where both 0 and 1 are absorbing barriers. When a gambler's pocket is empty, he's at 0, and his aim is to somehow get n rupees. And in every gambling move, he either wins or loses a rupee. And that's the gambler's ruin problem. And you want to figure out the probability that he's ruined or whatever. So here we want to figure out, in this random walk, our goal is to figure out the number of moves made to get to n. So the number of moves is going to be a random variable. So I am interested in the expected number of moves, okay? The average number of moves. So the goal is to figure out the number of moves made to get to n, starting where? Starting at any state j. For 0 less than j less than n, xj is half of 1 plus xj minus 1 plus half of 1 plus xj plus 1. With probability 1/2, I move one step closer, one step away, sorry. So I make 1 plus x, I need one move to do that, and then I need to make xj minus 1 moves. Or with probability 1/2, I move closer. Okay. So this of course can be rewritten as one sec. Shouldn't the second part be?
xj plus 1 minus 1, half of xj plus 1 minus 1.
Why? So let's take the expectation now. So so I want to denote the expected value of xj by a number hj. So by linearity of expectations, which we saw in the morning, by taking expectations, I know hj is the same as half hj minus 1 plus half nj plus 1 plus 1. Okay. So let's do some simplification in order to figure out how to deal with this. So there we know that, we also know that hn is 0 and h 0 minus h1 is 1. Okay, so xj is the random variable. Yeah, recurrence I have written for the random variable, and then I have taken the expectation. I can write the recurrence for the random variable as well. So this is when after I take the expectation. So let's simplify. So 2hj minus 2hj is hj minus 1 plus hj plus 1 plus 2, and what I get is hj minus hj minus 1 is hj plus 1 minus hj plus 2. Okay. So this is h0 minus h1. See, intuitively it's clear that h0 is going to be the largest and so on. So let's turn things the other way around. How do I flip everything? I'll bring this here because this is positive. hj minus hj plus 1 plus 2 minus 2 is also, or I'll take 2 to the other side, equals hj minus hj minus 1 plus 2. Is that right? Oh, so I should have plus 2 here?
No, just this first hj minus 1 minus hj.
hj minus 1 minus hj, I see. Okay. So now let's try to solve this recurrence. If you plug this in here, what do we get? You plug in for h0 minus h1, you'll get, so here let's plug in h0 minus h1, you get h1 minus h2 equals 3, and then h2 minus h3 equals 5, h3 minus h4 equals 7, and so on. And in the end I know, so I'm going to get hn minus 1 minus hn equals, what is this? 2n minus 1. So if I add up everything, I get h0 2n plus 1. It looks like 2n minus 1 to me. 2n minus 1. So h0, therefore if I add up everything, I'm going to get h0 is 1 plus 3 plus 2n minus 1, which is just n square, no? This is just n square. So h0 is n square, you can figure out that hj is bounded by n square minus j square or something. So let me just write that down and you can check it for yourself. N square minus j square. Because then you just have to pick those things in the summation and add them up. So it will be the tail of that sum. So the expected number of moves, if you start anywhere to get to the absorbing barrier, is quadratic, okay, order n square. So this is a well-known thing, and what Papadimitriou did in his little algorithm for 2SAT was to just use this to give a very simple randomized algorithm for 2SAT. And this particular algorithm, which we are going to finally discuss due to Schoening, was just an observation that, you know, a very interesting tweak to the Papadimitriou algorithm, which gives that algorithm. So let's first discuss Papadimitriou's 2SAT algorithm. Are you all with me so far? So the key thing that we have done here is that we have just analyzed this random walk only to figure out the expected number of moves that it will take to get to n. And that's quadratic basically. So now we're going to look at the 2-sat problem, which actually is in polynomial time, and you can see easily that. So F is a propositional 2CNF formula where every clause has exactly 2 variables in it. So C1 looks like maybe x1 or x2 bar. And so there are different ways in which you can solve the satisfiability problem in deterministic linear time. Or you can make a graph, a directed graph out of it and solve it by a kind of reachability problem. Okay. Strongly connected, you're finding strongly connected components, it amounts to that. But here is a very simple randomized algorithm, and that's a nice way of thinking about it. So I'm going to keep this and erase this. We already know the expected analysis which is there. So how does the random walk business come in when you're looking at 2-sat? So the setting is the same. Papadimitru says that, okay, let's assume that F is satisfiable. If F is, since we're going to find satisfying assignments, the goal is to find a satisfying assignment. If F is not satisfiable, you'll never find a satisfying assignment. So whenever you stop, you will say the formula is unsatisfiable. What you're really interested in is that if F is satisfiable, you want to find one assignment with high probability, satisfying assignment. So therefore you assume that F is, suppose F is satisfiable, F is a 2-sat instance, and A star is the satisfying assignment. Okay, so our goal is to get to A star. And this random walk, our goal was to get to N. So N stands for A star. That means you want to get an assignment which agrees on all coordinates with A star. So the number of matches that you have with A star is J. If you have J matches, you are in state J. Okay. So what should be the algorithm? Algorithm is the following. So start at any assignment. Let's call it B. What do you do? If FB is 1, then accept and stop. Otherwise, we know that B is going to falsify at least one clause because it's not a satisfying assignment. Else pick any CI falsified by B. Pick one of its variables uniformly at random. So you flip a coin to decide whether you're going to pick x1 or x2 and flip its value. To get new B, and then we'll go to 2 again. That looks horrible. Okay. Yeah, but go to 2 looks really bad here, but it makes sense. You just go back here and you repeat. Number of times. I'll analyze the algorithm and argue that with high probability in quadratic time, it's going to find a satisfying assignment. So yeah, you're right. what we'll have to do is that you repeat it for some constant number of times, n square number of times, and if you don't find a satisfying assignment, declare it's unsatisfiable. Okay, and since this closely mirrors the random walk on the line, if it were satisfiable, there is really an A star which is sitting there, then you will get to it with high probability in some constant times n square steps. So the key thing is to ask, why does this closely, how does this mirror, I mean this capture, the random walk capture the behavior of this algorithm? Yeah, but there are other things that are happening here. One of the things that is happening is that if I hit upon a satisfying assignment, I am going to stop. Okay, and there is another thing that could happen. Both the variables in the clause Ci may take the opposite value. So in either case, I may be actually going closer. So this particular step is not quite true for this random walk, because it may happen that Ci in the final satisfying assignment, both x1 is true and x2 is false. So in both cases, I may get closer. So what I need to argue is that the random variable that I define for the algorithm, the corresponding random variables to these xi's that I define, they will behave at least as well as this. And since this, the expected value of hj is n square minus j square, the corresponding expected value there is also going to be bounded by n square minus j square. That's what I need to argue. So how do I, so let's formalize what I just said. I'm going to use this part now. The other thing here is that the algorithm doesn't see the state j. There is no j that is visible to the algorithm. J is implied, I mean indirectly implied by the current assignment that you have. The state is actually the current assignment that you have. And j is an unknown parameter. It's the distance from that assignment, not the distance, the number of matches between that assignment and A star. Okay. So if B is the current assignment, the current state is j, which is equal to number of places where B and A star agree. Okay, so I want to define random variables yj. So there could be several assignments that match with A star on j places. Okay, and different assignments could take, starting at that assignment, I may take a different amount of time to get to A star. I'm going to take yj to be the worst among them. Okay, what do I mean by that?
J, but J is supposed to be very small, the worst case.
Yeah, so and what do you want to say exactly?
The worst case, Yj will be like the starting of the point where both B and G shall agree. It's just the beginning.
In the worst case,
Yj, we just maybe very small number of places where B and
see, Yj is going to stand for the number of steps that the algorithm takes if it is at distance j, if it is at an assignment which is at distance j from A star. Okay. It is the Hamming distance. So suppose you take it as the Hamming distance of the current assignment. So let's try to write down. So let's say Yj is the number of moves or the number of flips the algorithm makes to get to a satisfying assignment. So what I want to argue is that it has to be better than xj in expectation. I want to argue that the expected value of yj is going to be better than the expected value of xj. So how do I argue that? The claim is that the expected value of yj is better than the expected value of xj. Xj is the random walk on the line, the corresponding. So xj is the number of moves you require when you are at state j to get to n.
Well, I mean, this is the clause is falsified, so it's like both say x1 plus x2 is 0, 0. So in the final assignment, one of them must be 1.
One of them must be 1.
So it must be 1, 0, 0, 1 or 1, 1. So in some sense, if you flip one of them,
You are going to get a.
Hamming distance will be -2 or like.
So you'll get either 2 steps closer.
Closer or one.
So you won't. So basically, it won't be worse than xj. That's what we want to argue. So let's just see what is the recurrence that corresponding recurrences that I can write down here for that. I'll erase this part. So it's clear that y0 is going to be 1 plus y1, because if I am at an assignment that disagrees with A star on all the positions, then if I flip,
Y0 means that there is no flips required to get the
y0 means I disagree with A star. It's the number of places I agree. 0 indicates the number of places I agree.
The way you have written here, it's the other way around, right? Number of flips the algorithm makes to get to a satisfying answer.
Yeah, but j is that number. Yj is the number of flips required to get to that to get to the satisfying assignment. Okay, so y0 is the number of flips required to get to the satisfying assignment, starting from an assignment that completely disagrees on all places with that. Okay, so I should write y0 is upper bounded by 1 plus y1. The reason is that it could be smaller. I could have found a satisfying assignment. Okay, and similarly, I know yn I know is 0. Okay, and for all the intermediate steps, I can clearly write yj is at most half 1 plus yj minus 1 plus half 1 plus yj plus 1. So this is the case, this is the bad case that could happen, that exactly one of the two variables in a particular clause has to be flipped to get to A star. What might happen is that both, when you flip either of them, you go to xj minus 1. Okay. So, I mean, you go to the j plus 1 state in either of the two cases. So it's at least as good as this. And because of the initial conditions and this condition, you can see that at every stage xj is dominating yj, and in expectation also it's going to dominate. So it's going to imply that the expected value of yj is ordered by the expected value of xj, which we already figured out is n square minus j square. Okay, so therefore this algorithm requires only in expectation at most n square steps. So if you run the algorithm for 2 n square steps, by Markov's inequality you know that with probability at least 1/2 you will find a satisfying assignment if the formula is satisfiable. And that is the simple algorithm of Papadimitriou. Okay. So what if I try the same thing for 3-sat? So let's go back to the 3-sat problem with which we started and figure out how to solve that now. So what if we apply this? What is the equivalent random walk if you want to apply this for 3-sat? The equivalent random walk is if I think of the line here as representing the distance from the target satisfying assignment, which is A star. So if I am at a satisfying assignment B, which is at some distance j, which agrees with at j places, then I know B is going to falsify some clause which has 3 variables in it, and it's possible that for exactly one of them I get a step closer to A star. If I'm not lucky, that's what might happen. That means I'm going to, so the way we have analyzed the 2-sat case, it's clear that the random walk on the line was a kind of worst case behavior which gave you an upper bound on the running time for the actual algorithm. So here the worst case behavior would be that a step to the right you take with probability 1/3 and a step to the left you take with probability 2/3, which means that the recurrence that we have here will change accordingly. So these two will be the same, but a crucial difference will be that you step to the left with probability 2/3 and step to the right with probability 1/3. This is the worst case behavior. So I'm just looking at the random walk here, because I'm going to use that to figure out how good an algorithm I'm going to get. I don't really know how to exploit the other aspects of the algorithm where the assignment itself plays some role which we don't know how to analyze anyway. Even in the case of the y's, we only bounded the y's by the x's. Okay, so this is the random walk that you have. Now if you try to do the same expectation analysis that we did earlier, let's quickly see what we get. So this is the random walk that we have, and let's say hj is the expected value of xj. And again I know that hn is 0 and h0 is 1 plus h1, and hj is now 2/3 hj minus 1 plus 1/3 hj plus 1 plus 1. So if we simplify, note that you're going to get 3 hj is 2 hj minus 1 plus nj plus 1 plus 3. So move things around. So we know that h0 minus h1 is 1. So how do we arrange things? Yeah. hj minus hj plus 1 is 2 times hj minus 1 minus hj plus 3. So there is a factor of 2 that is coming in, which is going to mess up everything completely. So what is actually happening? So you plug in h0 minus h1 here, you get h1 minus h2 is 2 times 1 plus 3. And then you will get h2 minus h3 is 2 times this, 2 times 2 into 1 plus 3 plus 3. So which is like at least 2 squared. This is more than 2 square, and so on. So something like what you get is hn minus 1 is going to be more than, no, hn minus 1 minus hn is going to be more than 2 power n minus 1. So if you add up everything, you will get h0 is some constant times 2 power n. So the drift that is in the random walk, if you're going to take a step to the right with only probability 1/3 and a step to the left with probability 2/3, you will take a very long time to get to the absorbing barrier. It's 2 power n time. That's as bad as the algorithm that tries all assignments. So this is not going to work. If you just try to mimic what Papadimitru did for 2SAT, it's not going to work. Okay, so the clever idea that Schoening introduced was, you try for some time. If you get too far away, suppose you are already very far away from the absorbing boundary, then it's pointless to continue the walk, because it's like fighting against a current when you're very far from the other shore. For every stroke that you make, you're going to be pushed back twice the amount. Then you might as well somehow fly up and start at a random point. Okay. So his idea was to not just wait for the expectation analysis to work out, try for some time. If things don't work out, stop the random walk, start at a random point again. Now he is going to choose a random point, randomly chosen point, not the all zeros or the all ones vector, because if you are very far away, you will tend to drift further and further away.
Very far away, you get comes back and you've tried for so long.
Yeah, if you have tried for so long and you haven't gotten to a satisfying assignment, the hunch is that now you must be very far away. That's a good point. That probably actually that's maybe a nice heuristic. It has to be analyzed though. So the way the analysis we're going to present now is very simple. You try for 3n steps this random walk. If you don't get to a satisfying assignment, just abort, restart, but at a randomly picked assignment, because a randomly picked assignment is going to be now at Hamming distance anything from 1 to n with uniform probability. You have a good chance to be closer as well, reasonable chance. It's uniform, and you'll see that in expectation things work out well. No. So what we'll see is the probability calculation that we'll see. We can only write down bounds. Okay, I can only analyze a small part of it. I can say that if I am at distance j, then if I walk for at most 3n steps, then there is a reasonable probability that I'll get to the satisfying assignment. Okay, if that doesn't happen, it's still only it's an inverse exponential probability, but it's not as bad as 1 by 2 power n. It's better than that. So there is a certain probability with which I'll get to the satisfying assignment, but I may not. It's a small probability only. If I don't get there, I'll stop the walk. So the question you're asking is, can you know how far you are?
Yeah,
Otherwise, you shouldn't. I don't know. I think those are nice ideas, but they need to be analyzed. I think especially what Kamal suggested makes a lot of intuitive sense. That if you know that you didn't get close, okay, then the hunch is that you're really far now, and so flip.
Okay. It may be just the opposite of what it is. So you can as well flip and try. Flip all of it and see if it is satisfying.
Yeah, isn't that same as what Kamal is suggesting?
So even if for this y0,
Yeah, you can refine the algorithm. Yeah, exactly. You can refine the algorithm, but can you analyze it to get a faster running time is the question.
by being completely opposite of all increase, it does not mean it is not a satisfying signal.
That also is true. That itself could be a satisfying sign.
It could even be done.
That's true. That's why we can only write down upper bound on all those random variables. So what is the algorithm that he has in mind? So let me just put down that algorithm here. So F is now a 3 CNF formula. Assume that it is satisfiable and A star is a satisfying assignment. And I need some more space, so I just created that. So here is the algorithm. First step is pick a random. So you pick a random assignment B. Okay, so instead of starting at any assignment. Second step, it's like before. If FB is 1, then done. Else, pick a falsified clause. Pick a variable at random and flip. Okay, so this you repeat. So go to 2. So this thing you do for 3n steps. If it doesn't work, you go to 1, and this loop you do for, let's say, some m steps. So what you've done is you've done the random walk for 3n steps. If you didn't find a satisfying assignment, you aborted the random walk, got out, and just picked a random thing, a fresh assignment again, and started the whole thing. So there is an outer loop which is running for m steps, and the random walk itself is running for 3n steps. Okay, so now it's not the number of steps that we're interested in, because you have cut down the number, you have bounded the number of steps. Number of steps is bounded by 3n in the random walk. So you're just interested in figuring out what is the probability. If I started at an assignment which is at distance j from the target assignment, what is the probability? Can I lower bound the probability of getting there within 3n steps? So that's the thing that we are interested in. M is not, yeah, okay, let's call it k steps. So it's a different analysis that we need to do now. Suppose B is at distance j from A star. let Qj be probability that in at most 3n steps we get to A star. It's a lower bound on the probability that in that loop you will find a satisfying assignment, because in between also you might find a satisfying assignment. So what is the probability then that in at most 3n steps we get to A star? You start, so this is n, you are starting at n minus j now. I am saying that the distance is j. I know that I need to make j right moves. In all, I need to make j right moves. And I know that I am twice as likely to make a left move as a right move. So let's try to figure out the probability that I make that in 3j moves. What is the probability in 3j moves? What is the probability that we make 2j right moves and j left moves? And this is something that I think you just arrive at by intuitively figuring out that you want to make enough right moves to get there, because the probability of making a right move is small, so you want to make enough right moves to get there. So what is this probability? It's just the binomial 3j choose j. The j left moves could be located anywhere. 1 by 3 to the power 2j, 2 by 3 to the power j. This is what what binomial distribution tells you. But what is actually happening is that some of these sequences you will not actually complete the run, because I may make 5 left moves and then I have a whole sequence of right moves. The moment I get here, I am going to stop. But those sequences, the set of all those sequences will actually add up to give you the right number. So I just want to stress that in the experiment, though it won't happen like this, you won't actually make all the 3j moves, some of them will abort. This is still the right probability calculation as a lower bound. It's only a lower bound because you have 3n steps in all, and this is one good way of getting to the right boundary. So the simple thing is that Qj can be lower bounded by this. Okay, now let's quickly figure this out and then we'll see Stirling approximation and then we are done. So this is 3j to the power 3j e to the minus 3j root 2 pi 3j, 2 pi into 3j divided by j to the j e to the minus j root 2 pi j, 2j to the 2j e to the minus 2j root 2 pi 2j times that quantity times 1 by 3 to the 2j, 2 by 3 to the j. Okay, now let me erase this and complete the calculation here quickly. The e to the minus thing will vanish, and the j to the 3j, you have j to the 3j below as well. So what do you have up there which you don't have below? You have 3 to the 3j divided by 2 to the 2j, and there is some constant time divided by square root of j extra. That constant, the pi and all, let's absorb into some constant. Say this is greater than or equal to 1 by 3 to the 2j, 2 to the j, 3 to the j. So this is just c by square root j 1 by 2 to the j. So if you are at distance j, what it tells you is essentially like 1 by 2 to the j is the probability that you will get in 3n steps. So there is a huge probability with which you would have drifted far away, but at least there is this small probability with which you will get there. But now it's crucially we are going to use the fact that you started at a random assignment. If you start at a fixed assignment, that if that is very far, you have no hope. You will be like 1 by 2 power something. So because you are starting at a random assignment, what is the expected? So the probability of getting to A star from a random assignment is just summation you are at distance j times, no, so what I mean is probability that the distance between B and A star is j multiplied with qj. It's at least this much, and j can be anything from 0 to n. Correct, no? Because you picked a random assignment B, you cannot be at distance. And what is this probability that you are at distance j? It's n choose j 1 by 2 power n. N choose j 1 by 2 power n. Because those j places where you will agree, and the whole thing has to happen with probability 1 by 2 power n. So this is n choose j 1 by 2 power n. So this is greater than or equal to, and we'll put in that c by square root j 2 power j. So the 2 power 1 by 2 power n comes out 1 by 2 power n comes out, and you have this funny thing, n choose j 1 by 2 power j. Let's take out the root j as root n, it doesn't matter. Those things won't change things much. So this is the crucial thing, summation n choose j 1 by 2 power j, that is 1 plus half whole to the power n, right? So the overall running time has turned out to be, I mean the probability is at least, right, 1 by 2 power n, square root n here, some constant, and that's 3 by 2 whole power n. This 2 goes in, so this is c by root n 3 by 4 power n. So this is the probability with which the inner loop, the 3n step walk, is going to get to a satisfying assignment. This is the lower bound on the probability. So to make the probability, what is the number of times you need to run it? 1 by this many times. That's what the outer loop should be. K should be that. If you run it that many times with constant probability, it will be there. So 1 by this is 4 by 3 square root n, 4 by 3 to the power n square root n. And the rest of the polynomial factor comes because you are doing something here. You are checking if f is true and you are picking a clause and some linear amount of work. So it's a very nice idea that everything boils down to this random walk on a line. And there was somebody here who was supposed to help me show a clip to end my talk. Ungalal mudiyuma. Watch the clip and then we will discuss. So you can see the straight line, random walk in the straight line. Raj Kapoor is the absorbing barrel. For those of you who don't understand Hindi, he's saying life is a random walk.
कहा हमने वैसा ही किया, दिल ने हमसे जो कहा हमने वैसा ही किया, फिर कभी फुर्सत से सोचेंगे खुदा था या भला जिंदगी ख्वाब है, ख्वाब में झूठ क्या और भला सच है क्या।
Stop it.
This summation term there, J is equal to 0 to n probability of having distance of B and A star is equal to J.
Yeah.
So does that say implicitly or about some having distances of number of strings which are having distances, or because
It's playing the role. Yeah, exactly.
yeah.
You can choose J, 1 by 2 power J is finally what is giving you the 3 by 2 power N.
But is there like any other explanation or which makes it
I don't know what happened.
yeah.
So in parameterized complexity, for instance, they're given a 3-sat formula, let's say, and you want to check if there is a satisfying assignment of weight at most k. How do you do it? By weight I mean the number of ones, Hamming weight 1, k. You can do it in 3 power k time. Can you speed it up using this kind of idea? So, I mean, if you want to make the Hamming distance count in some way, maybe this is a problem that you can think about. I don't know if you can use it really. Because you'll just do that simple 3-way branching and
Which are those key variables? Right, but those two, but those two be any among n variables, those two any k variable.
yeah, but it's
You will pick a clause, and you know that one of them has to be set. So you branch. That's a 3-way branch.
so you start with the all zeros which will fall.
All ones. There is no such clause. You can set them all 0 and do that.
Now you want Hamming weight at most k, so you'll start with something that has all zeros, and then you will make things 1 as you.
Random. So for 3 power k, I'm just saying you start with a class where all variables are 1.
Yeah, but that's Hamming weight very large.
See, if everything is 0, then you can even set them all to 0. Whatever.
Right, that's why I'm saying we can start with the all zeros assignment.
For your random.
Now even for a Hamming weight at most k algorithm, shouldn't you start with something that is all zeros and then make things 1 as you, the number of, the weight, not Hamming weight, the weight, the number of ones. That's Hamming weight of a vector.
Start with all zeros and then
But it's guided by a falsified clause, so the branching is always 3-way. But can you speed it up using this? I don't think it's known.